Okay, now we'll see the rheological behavior of the fluid. So rheology, one department where we are discussing about the properties of the fluid. So the fluid is which kind of the fluid, whether it is obeying the Newton's law of viscosity or it is not obeying. In such a way, we will classify the fluid. So basically, first classification, we are going to say here, those fluid which obey the Newton's laws of viscosity is known as the Newtonian fluid. Newtonian. Such an example, if you're telling about the example, water is a Newtonian fluid, air, diesel, etc. These are the Newtonian fluid. It obeys the Newton's laws of viscosity. And those fluid which does not obey is known as the non-Newtonian fluids. So to classify the non-Newtonian fluids, a model has been taken. This model, name of the model is the Oswald-de model. You'll see the model now. Oswald-de model. It is another name is the power laws. Sometimes it is telling about the power laws. In the power law, the shear stress is proportionate to the rate of shear strain in terms of some index. Power is there. So to the power some values. This n is known as the flow behavior index. This n. So in the broader explanation, if you write it here, this equation will be looks like in this way. Equality sign. They're just like. So here, this K is known as the flow consistency index. And what about the B? B is causing for the initial stress. That means if some initial stress is required to create the flow, whether for such kind of the fluid, we require some initial stress to create the flow, just like some gel or some paste. We give some initial force, then only it is going for the flow. So that is some initial stress value. Initial shear stress. So also a de model in this way. From here we are categorized the fluid. So let you take some fluids. Normally, from the ideal fluid definition, we did not give some initial stress. We do not required to give any initial stress. If you give a small amount of the shear stress, it will automatically start to flow. That is the definition of the fluid we know. So B value, in case of the most of the fluid, this B value is taken as the zero. We need not to give any initial stress to create the flow. If some infinitesimal small amount of stress, shear stress, if you give the fluid is starting to flow. So most of the case, the B is equal to zero. So this equation, power laws equation, reduced to in this way. Now here, this K, we can write it in this way. Rate of this theta dot is the rate of angular deformation or rate of shear stress. So we can split this thing in this way. So this K, if you recall your Newton's law of viscosity, we have written it in this way. U into du by dy. Whereas this theta dot is nothing but is equal to du by dy in our case also. So this term is known as the apparent viscosity. So just it is a convertibility of the power laws in terms of the Newton law of viscosity. But the viscosity here, what the viscosity you are getting, that is not a constant. Previously in that case, it was a linear relationship. That's why it is a constant. Dynamic viscosity was a constant. But here, the apparent viscosity is not a constant. It is depends on the strain rate. That means it's a function of theta. So if you change the theta dot, the apparent viscosity will also become changed. By this way, we are doing the classification in here. What kind of classification? So this n value, if greater than 1, we'll get some kind of a fluid. If n value is equal to 1 and n value is less than 1. Three cases we'll see now. What are the three cases we are talking about here? So again, rewrite the equation. Tau is equal to the Power's law's equation. Mu apparent. What is the mu apparent? For the power laws, we are talking about the power laws here, or Oswald d Walla equation. That is nothing but the k theta dot n minus 1 is the apparent. So case 1. Case 1 is the easy case. If you take n is equal to 1, take n is equal to 1, so simply your equation reduced to k into theta dot. And k is equal to mu, constant, both are constant. So the equation reduced to the Newton's law of viscosity. Hence, you are getting those fluid. For those fluid, the flow behavior index is equal to 1. This fluid is nothing but the Newtonian fluid. Those fluid, this index is 1, n is equal to 1. Those fluid are nothing but the Newtonian fluid. If you plot such fluid in this graph, the graph is the along the y coordinate you can see here. That is a shear stress we are plotting, and along x coordinate, the theta dot you can write it here. That is the rate of shear strain you're plotting here. So Newtonian fluid, that is the linear equation it is getting. Newtonian fluid equation, you have seen it, is tau is equal to mu into theta dot. So it's a straight line equation and mu is a constant. As the mu is a constant and it is going through the origin, of course. Because if theta dot is equal to 0, so mu is equal to, tau is equal to also 0. So here in this case, your Newtonian fluid will be this. Is the n is equal to 1 or This is a plotting of the Newtonian. Next case, we'll see here the case number 2. N less than is equal to 1. So if n is less than is equal to 1, if you see the apparent viscosity is decreasing in nature with the increase of because your equation apparent viscosity is k theta dot n minus 1. So as n is less than 1, so if you increase theta dot, your apparent viscosity will decrease. So such a plot, if you're putting the plot in here, in this case, you plot it here, the in this way. So this is the plotting of the n less than 1. This kind of the fluid name is the pseudoplastic. Where apparent viscosity is decreasing with the increase of the rate of shear strength. So if you go along this direction, if you go along it, you see the slope is decreasing continuously. So in that case, the slope here, whatever the slope it was in this point, with respect to in this, now if you take here the slope and here the slope, definitely in this position, the slope will be less than the previous one. So slope is continuously decreasing. So apparent velocity is continuously decreasing. So this another name is the shear thinning. This kind of the fluid is known as the shear thinning also. It's the example of the pseudoplastic. Next case, the case 3. If n is greater than 1. If n is greater than 1, so apparent velocity, you see n minus 1. So if you increase the theta dot, your apparent also. So it is a shear thickening. So if you increase the theta dot, your apparent viscosity also increasing in nature continuously. This kind of the fluid is known as the dilatant fluid. This kind of the fluid is dilatant fluid. So how it will be looks like, this dilatant type of the fluid will be looking in this way. That is, n is greater than 1. Dilatant fluid. So apparent viscosity is continuously increasing. Slope is increasing. If you go along this way, the slope is continuously increasing. So shear thickening this way. So this types, this case 2 for non-Newtonian fluid, case 3 also for the non-Newtonian fluid. Both examples are for the non-Newtonian fluid. If you go for the example of this case 2, there are some sort of example will be here to be given. That is the pseudoplastic fluid. The one example is the blood, human blood, where the n value is roughly 0.7. But it will vary with the composition of the blood and so many other factors there. But blood is definitely a non-Newtonian fluid, and it is a nature is the pseudoplastic. That means the apparent viscosity is decreasing with the shear stress. So blood is one example for this case. Another polymer solution is also other example for the pseudoplastic fluid. Similarly, the dilatant fluid having so many examples, just like the honey is the dilatant fluid examples, and there are other examples also will be given one by one. Sugar solution, butter solution, this is all the example of the dilatant fluid. Now the next part we'll see here, the Bingham plastic fluid. The Bingham plastic fluid, the case 4, we'll talk about now. Case 4. In that case, the case 4, whenever we are taking, we write down the first equation, whatever we have seen, getting it from the Paul-Law's equation, also a Diagonally model, the same thing we are writing. In this case, what is happening? The B is some initial stress. So some fluid is required some initial stress, then only it is starting to the flow. And N is equal to 1. So in this kind of the fluid is known as the Bingham plastic fluid. After giving a certain stress, the plastic behavior you could be able to see. So if you plot this kind of thing in here, so you require here some initial, and it will be like this. So this is the initial stress is required here. Amount of the initial stress. That is nothing but the 1000. Then it is behaving like a Newtonian fluid. So this is a Bingham plastic fluid. Example is a toothpaste gel. In this kind of example, it comes under this fluid, Bingham plastic. Now we'll see one more important thing here. About this way, this axis, x-axis, abscissa. What does it mean? That means that tau is equal to 0. Tau is equal to 0, no shear stress, but continuously it is deformed. Continuously it is deformed. So ultimately, there is no shear stress, but deformation is continuously along this axis, along the abscissa I'm telling. So this is the definition of the ideal fluid. So I'll come some definition of the ideal fluid. Ideal fluid means those fluid having no viscosity, no dynamic viscosity. One more thing, no surface tension. Will come the next topic, the surface tension, no surface tension. So in viscous, no surface tension, and incompressible. Incompressible. So ideal fluid means without any shear stress, it is continuously deformed because the viscosity is 0. As the viscosity is 0, so whatever the value of the theta dot tau will be equal to 0. So this abscissa, you can consider the plotting of the ideal fluid. And what is about the ordinate? In case of the ordinate, so how much shear stress you are giving, you can increase the shear stress at from a 0 to at some higher values. but the theta dot value is always 0. Rate of shear strain is 0. That is for nothing but ideal solid. Non-deformable solid. So how much shear if you are giving, still no deformation is taking place. So this ordinate is the plotting for the ideal solid. And this abscissa is the plotting for the ideal. So this is the total graphical representation in this case we are considering. So some problem we'll see regarding this topic, the viscosity topic. And before going to the problem, I just telling some concept here. That is the linearization of the Newton's laws of viscosity. So here we are giving some linearization of the Newton's laws of viscosity. Of Newton's law of viscosity. This topic we'll see very small time, and we'll come to the problems regarding this topic. So Newton's laws of viscosity, the formula we are getting it in here, du by dy. What is that? That means if you consider the two layers, there's the first layer and the second layer. In between these two layers, the dy is the difference, and the velocity, if it is here u, if it is here u plus du, then only you could able to write this equation. Now the linearization is if the gap is very small. So here, what is the plotting? Here the velocity was plotting was like this, non-linear form. The velocity plotting, if you plot the velocity diagram, it's a non-linear in nature. Non-linear plotting. But if you plot the velocity in this way, in the linear pattern, if you could be able to plot the velocity in the linear pattern, when it is possible to, when the gap between two layers is sufficiently small. It may be in mm scale, millimeter scale, or it should be nearly some 1 centimeter, maximum 10 centimeters, not more than this. In such a case, you can consider the velocity profile here is the linear profile. As the velocity profile is the linear, if you're considering, then you write it down in this way, this tau. Let you take here, the velocity is 0, and here the velocity is v, and it is a linear profile. So what is the slope of this profile? The slope is nothing but here, du by dy is equal to e minus 0, and the gap, let you take h. So h minus 0. So here consideration is the linearization of the Newton's laws of viscosity. So you can be able to write it u into d by h in linear form. So the gap should be sufficiently small. If the gap is sufficiently small, you can consider the velocity profile is a linear profile. And if you could be able to compare this is a linear profile, then there is no more discrepancy in here. No more discrepancy. Let you take two plates here. Two plate. There is a one plate, is a fixed plate, and this is another plate. In between, there is some fluid. The top plate, the bottom plate. Now the top plate is moving with some velocity u. This kind of the flow is known as the Couette flow. Why we should study Couette flow? Because it will give the idea of the bearings or some viscosity meter also. To find out the viscosity of the fluid, the viscosity meter we have to use. Viscosity measurement if you want to do. So we are not going to the details of our viscosity measurement here, just giving some ideas of the linearization. So here also, if the gap between two plates is the h, so the slope du dy, you would be able to write it u minus 0 divided by h minus 0, so u by h. So you can be able to tau is equal to u by h. That is the linearization of the viscosity, Newton's laws of physics. This idea is required for the some kind of the problems. If the gap is given very small, you can apply this formula in here.